Eu não sei se vocês estão vendo, dá para ver pela internet? Ok. Boa tarde a todos. Então, hoje nós vamos ter um novo seminário aqui no Departamento de Ciências Atmosféricas, aqui do IAG-USP. Nós temos o prazer de ter como convidado o professor Nicolas Hall, da Universidade de Toulouse, e que vai falar sobre previsão sazonal de chuva no Brasil. Muito obrigado.
Obrigado.
I would like to thank you for accepting the invitation for this seminar.
Já cumpri tudo.
Já.
Tá bom.
Thank you.
Ok. Olha o microfone. Ok. Posso continuar em português? Começo a aprender um pouco de português porque moro agora na Fortaleza há mais de um ano. Mas acho ainda fazer um seminário de 1 hora em português, de inglês, transformará seminário de 3 horas em português. Mas eu vou continuar em inglês. Próxima vez. Não sei. Sim. Ok. So, just to start with, this is my COVID test from yesterday. So, I don't have COVID, right? So, if you don't mind, just to give this talk, I take this. Because it's very difficult to speak to an audience with this damn thing on. So, so as I said, I live in Fortaleza, and I'm very lucky to live in Fortaleza.
Ô, Richard, não dá para ver nada.
Não entendo nada.
Não dá para ver.
A tela
I
tá
cannot
toda
see.
azul. O Richard? Não, é para ele.
A tela tá no YouTube?
Não, eu estou no Google Meet. Não, não dá para ver, Rose.
Tá bom. O Richard, cadê o Richard?
O problema não é esse.
É que assim, eu fiz pensando em usar o computador desktop daqui, o notebook.
E agora?
É só no YouTube.
Fala pro YouTube. Ô, Fábio, tá ouvindo?
Não, eu estou no Google Meet.
Mas vai pro YouTube.
Você consegue ir pro YouTube?
O que tá indo pro YouTube é o que tá indo pro Google Meet.
Não, ela tá conseguindo enxergar no YouTube.
Então, mas é que eu tô filmando assim, ele tem que ir lá na câmerazinha e colocar em evidência. Mas assim, não vai ficar boa a qualidade, vai ser qualidade limitada àquela câmera lá. Eu tô filmando aqui.
Não tem muito o que fazer.
Não quero fazer.
Não tem muito o que fazer.
Assim, a outra opção seria ele pegar os slides, colocar nesse computador.
Dá pra fazer isso?
Can you put your presentation in the computer?
No, that's out of the question. This is a keynote presentation for Mac. So,
No YouTube tá passando?
Ele tá filmando.
No YouTube tá.
Vai pra lá.
Ou então, quem tiver no Google Meet, por favor, vai pro YouTube.
Ou então,
Tá bom.
em evidência a
Ou
câmera.
coloca o pinzinho da
Coloca o pino na câmera que tá apresentando.
para ela ficar pelo Ok, Nick.
Eu, Fábio?
it's okay.
Só que você tá invertido, tá? Como se fosse espelho.
Thank you, Fabio. Do you have any more questions, Fabio?
Yes, I do. It's like a mirror. I see you in no position, all in the mirror.
Oh,
It's a mirror like...
it's a mirror image.
Mirror image.
Well, get a mirror and put your computer in front of the
Oh,
mirror.
yes. That can be. If I find the one, I can do it.
Go to the bathroom. Watch it in the bathroom.
No.
imagem está espelhada no YouTube.
Mas como ele está usando a câmera, talvez ele tenha que ajustar ali, né?
Não, é na câmera. Na hora de
Ah, tá.
tem um delay. Inverteu? Vamos ver, tem um delay. O Fábio é que tem que... Ah, não, talvez ele já tenha ido para o YouTube. Eu estou no YouTube agora para ver. Alô?
Ele vai responder lá, né? Você saiu.
Você depois foi no YouTube. Não, acho que agora tá bom, deu certo. Deu? Eu tô vendo certo a imagem. Você tá vendo, Raquel? Tá certo. Ok, good. It's okay now.
Okay, everybody happy?
Start again.
Okay. Well, I hadn't started, so yeah, I'm very lucky to have this opportunity to spend a couple of years in Fortaleza, where I'm working at Franceme. So Fortaleza is quite a nice place. This is the view from my apartment, and the idea here is to predict the rainy season in the northeast Brazil. So if I just play the time lapse, you can see the rain arriving in the north coast of northeast Brazil. And our challenge then is to predict the rainy season, how it changes from year to year, using a simple dynamical model, because they already have a fully fledged GCM prediction system. So what can we contribute with a simple dynamical model? The model I was using when I was here a few years ago, we have now developed it to the point where it can produce rainfall and it can respond to sea surface temperature anomalies. And so the procedure is to look at the different sea surface temperature anomalies from year to year and see how that affects the continental rainfall that is produced by the model. So that's my work, and start with a quote. It's tough to make predictions, especially about the future. So this is there's a famous baseball commentator called Yogi Berra who said lots of funny things. And so on the face of it, you'd think that that's funny, right? But in fact, Yogi Berra didn't know anything about physically based ensemble hindcasting systems. He knew a lot about baseball. And in fact, it turns out that if you have a physically based system, making predictions about the past is just as difficult as making predictions about the future. So I'm going to show you both, okay? Well, first of all, here's my dream team. So these are the top row is Franceme, Brazil. Okay, there's Mary, Junior, and Letitia. That's in Franceme. And Oberhens is now professor at the University of Ceará, and Duarte, a student there. Bottom row is my French associates. Well, they're not all French. You can guess which one isn't. So here's my prediction. I go straight to it, right? This is my prediction for we made this prediction at the beginning of January this year for the rainfall anomaly. And this is for January, February, March. So this is the total accumulation over 3 months, January, February, March, using DREAM. And so what you see is we predicted. So this is our prediction. We issued it early January. We predicted that it would be wet over the extreme northeast, a bit drier further north, wet in the tropical Atlantic, the northern hemisphere, dry in the southern hemisphere, and slightly wet over southern Brazil. So how did we do? Here's the verification. So what happened? Well, this is wet. This is wet. This is dry. Okay, it's a bit drier up here. Here we didn't do so well. Okay, but I think that I would like to claim that that's quite a good prediction for a three-month forecast, and that's as far as we predicted to the end of May, but that's as far as I have validation data for the moment. So it looks like DREAM produced a forecast that was reasonably accurate for this year, right? How do we do that? How do you do that with a simple dynamical model? So the first part of my talk will be describing how we do that and showing some idealized examples. And then towards the end of my talk, we'll go back to the predictions, and I'll show you some predictions for previous years, because we've done a whole sequence of predictions, and see how good this model really is. Did we just get lucky here, or is it useful as a prediction model? So quick spoiler for that is it's not that great. It's not as good as it looks here, right? But it's got potential. So how do you do a seasonal forecast? Well, you start with a mathematical problem, okay, and an initial condition, which is global, and a forecast product, which is more regional. The mathematical problem consists of some fluid dynamics and some atmospheric physics, okay, and a big part of the prediction depends on sea surface temperature anomalies, which are persisted throughout the forecast. Then you have a wide range of initial conditions because you do an ensemble forecast. It gives you a wide range of forecasts from which you can deduce means, distributions, probabilities for your forecast product. Okay? So that is basically how it works with a traditional GCM-based forecasting system. This atmospheric physics part, radiation, convection, all that kind of stuff, is quite expensive in terms of computer time, right? To run the ECAM model, which is what they use in FUNSEMI, on the FUNSEMI computer system, 1 hour of forecast for a single member, sorry, one month of forecast for a single member takes an hour of computer time, right? So we have the DREAM system, right? DREAM stands for Dynamical Research Empirical Atmospheric Model. So it's the key word there is empirical. We use some idealized forcing, which is deduced from observations, from a long time series of observations. And we use it to replace this atmospheric physics part. We have a big data set. We produce an empirical forcing. There's no physical parameterizations in DREAM, apart from some very basic drag, and I've added a convection scheme, right? And so that means, that instead of 1 hour, it takes 1 minute. So that's a fairly dramatic improvement in computer efficiency, which allows us to do a range of things. We can do all sorts of tests and academic studies. So it's a research tool, which we're also using for forecasts. What are we using it for at the moment? Well, the influence of MJO phases on the initial condition, that's Letitia's project. Role of different tropical ocean basins in northeasterly rainfall, that's me with Aubens. Hydrological sensitivity in northeasterly catchments, that's Duarte. Interhemispheric wave propagation to the SACZ. I can't remember who's doing that. No, it's Hugo, of course. Nonlinear response to El Nino and rainfall over Vietnam. That's Margot and Han, not related to South America, but that's the set of things we're doing. It runs fast, so we can use it as a test bed for forecast strategies. And we're developing it into a potentially useful community tool for research and training, for operational activity, etc. Okay, so how does it work? So this is my brief summary of the way in which we use data to force a dynamical model to behave like a GCM. And so imagine you have some sort of generic time development equation. So Q could be anything, could be potential vorticity, whatever you like. You have the advective dynamics, and on average, that advective dynamics is balanced by by forcing and dissipation, right? The forcing is considered to be external, right? If we consider a model now which has these elements, it has the advective dynamics, it has some prescription for the dissipation, can we replace this external forcing, which is like radiative forcing, surface boundary conditions, etc.? Can we replace that with some empirically derived forcing function, G, right? And you can use data to generate G, right? You can say that G is the mean of F, right? You don't know F, but you can find it. You can find F, the mean of F, by just running the model with no forcing at all, okay, for one time step. And you do that for a large series of initial conditions. Take the average of that tendency that you get, and that will be the negative of F bar, okay? So you can find G equals F bar equals the average of all these single time step predictions, or you can write it like this, okay? So that is our G is then our empirical forcing for a simple GCM. We can apply it, and then we apply a perturbation to the sea surface temperature. I'll explain how that works next, but here, basically the idea then is that we have a control model and we have an experiment, okay? So this whole forecasting strategy depends very much on running control runs and then perturbation runs with an anomaly in the SST. It's the anomaly that counts, right? That's where it's different from a traditional GCM forecasting exercise. So the dissipation in the model is very simple. It's just a boundary layer drag. It's a vertical diffusion scheme, actually, where the coefficient is stronger in the boundary layer and very weak in the free troposphere. And there is a constant relaxation or radiative convective relaxation, 12 days constant for that, 16 hours average in the boundary layer, dropping to 20 days in the free troposphere for momentum. So this is momentum, this is temperature. That's all there is to it for our dissipation. So how does it work? So this is actually some results that I produced last time I was here, when we were interested in the annual cycle. And so on the left-hand column there are the 4 months, the 4 seasons, sorry. And this is the era interim reanalysis for upper-level zonal wind. And this is the model simulation. So you can see that it's a fairly good match to the observations. If there is a systematic error in our model, it is in the southern hemisphere jet in the southern hemisphere winter is a little bit too strong. So that's the upper level zonal winds. We also have the upper level momentum flux. And again, you can see that it produces storm tracks which look fairly realistic. They are slightly weaker than they should be in the summer, in the southern hemisphere, sorry. And the lower level temperature fluxes, so the storm tracks at the beginning of the storm tracks, we have, again, a fairly realistic distribution. The right-hand column is just perpetual versions of the cycle here. They're not very different. And so I believe here we have a realistic basis for doing experiments with this simplified GCM. Now, we have a convection scheme. So DREAM can be run with a scheme for large-scale rain and deep convection. The deep convection interacts with, so if you enable the deep convection scheme, you can produce rainfall with the model. So this is the March, April, May climatological precipitation from DREAM. This is the observations. So what do we see? We see rainfall over South America. We see the ITCZ. We see the intense Indonesian region with the SPCZ. We also have an SACZ. We have most of the features of the rainfall for that season. compared to the GPCP data, our rainfall is slightly weak, but it's well distributed. All right, so that's our basis for making forecasts. Now, so then the forecasts, how do we do it? The model needs to respond to a sea surface temperature anomaly, right? So what we do is we have an anomaly in sea surface temperature. In principle, that creates deep convection, which will then lead to diabatic heating deep in the troposphere. That heating will produce a dynamical response. The dynamical response will then affect the model rainfall over the continent. So that's the kind of chain of causality. And so we need to think about how we do that in detail. So here's how we get from the first step, from the SST anomaly to the rainfall. And so I've used a few kind of canonical SST anomaly shapes for the Pacific. So this is based on some of our work with El Nino. So 3 different kinds of El Ninos. And can we reproduce the precipitation response to those El Nino SST anomalies by prescribing a simple function? So these are the SST anomalies. These are the associated precipitation anomalies observed. And then we run these SST anomalies through this transfer function. Now, that's a nonlinear function. It depends on the climatological sea surface temperature. It also depends on the anomaly in the sea surface temperature. It depends on the divergence and on the climatological divergence. So that's the divergence anomaly. And this has been put together by Srinivas et al., who have just submitted this to Journal of Climate. And so we're using a simplified version of their work for this. This is an empirical transfer function, so some of the parameters here have been just deduced from data. And so these are the rainfall patterns we get when we apply this formula. So they look sort of like the observed rainfall patterns, so we'll say that's our transfer function. We need to go from that precipitation estimate to a heating, right? So then we need to heat the troposphere or cool it, depends on the sign of your anomaly, right? And that's a simple change of variables, right? There's a simple formula that goes from precipitation anomaly to heating rate, and it depends on a bunch of thermodynamic constants, okay? It's just changing the units from precipitation to heating rate. And then we have to decide how to distribute that heating in the vertical. So we do it using this fairly simple formula to make it look like the heating associated with deep convection, right? So that's how we put that heat source into the model. From then on, the dry dynamics of the model takes over. This convection scheme in the model responds to those anomalies in the circulation, and we produce a forecast. So before I show you the forecasts, I'm going to talk about a few sort of academic idealized cases. Right? So here, we've decided to look at an idealized Atlantic dipole in sea surface temperature. Now, if you look at the deep heating associated with that, using the method I've just described, it's no longer in the same form as the SST because, well, that transfer function, it depends not just on the SST anomaly, but also on the climatological SST, right? So where the SST is warmer, that's where the anomaly is going to be more effective. If you heat where it's already warm, you'll have a bigger response than if you heat where it's cold. So that brings the heating anomaly closer to the equator, okay? And so for a positive dipole, warm here, cold here, you get heating here, cooling here. We also did the opposite, cooling here and heating here, right? So then the question is, how does the model respond to that? And, well, to start with, this is not using the full GCM to start with. To start with, we're using this thing called GBS, which stands for basic state. This is a stationary wave model prescription. So it's not quite the same as the GCM prescription. What it does is it holds a basic state in place, and you can do linear stationary wave solutions. And I've actually found a way of doing a time-independent linear solution to a perturbation on a fixed basic state. This is a March, April, May fixed basic state. So this is in the dry version of the model. So there's no rainfall, but you can still look at the vertically integrated moisture convergence. We still have a moisture variable, but it is a passive tracer. So this is just to see what is the effect of dry linear dynamics alone responding to these SST anomalies. And you can see that if you have heating here, cooling here, then you have convergent moisture flux here, divergent here. So this is wet, this is dry. This is a big dry patch here, big wet patch here. The opposite when it's the other way around, okay? And note that the contour interval for this moisture flux convergence variable, it varies between plus or minus 0.5 millimeters per day, so that's quite weak, okay? I've blown the contours in over the SSTs, but over the continent it's quite weak. Okay, what's next? Let's turn that into a forecast. So instead of you doing a time-independent solution on a fixed basic state, let's run the GCM. But we'll run it in dry mode. It's still a dry model now. And we're still looking at moisture flux convergence. So you can see that it's much noisier, because now this is a forecast run. It's a March, April, May forecast run. So we start the forecast on the 1st oh no, sorry, this is an equilibrium run. This is still it's a long run. It's a 500-day run of the GCM. So it's not a forecast. It's perpetual March, April, May. And you can see that the response. So now our contour ranges from -1 to 1 millimeters per day. So it's double what we had before for the stationary wave solution. Even though it's still dry, having some transient phenomena in there has actually amplified the response. So that's interesting. And we now have some appreciable anomalies of the same sense over South America, much noisier, because now this is a fully transient GCM. This is the climatology from that run. This is the control run. Okay, so there's our ITCZ and our rainfall over South America. And these are our evaporative source regions. Okay, and then these are the anomalies: wet, dry, and then dry, wet. So that's with the dry GCM. Now let's switch on the convection scheme, okay, and see what the wet model does. And so this is the wet GCM. And now the contour interval goes from -2 to 2. So we've doubled it again. So having an interactive moist convection scheme in the model amplifies the response again compared to the dry model. And we still have a similar kind of pattern: dry, wet, wet, dry. Still looking at moisture flux convergence. Okay, but we can also now look at rainfall, because we have rainfall now in the model. So here's the control precipitation rate. Here's the precipitation rate for a long equilibrium run of the moist. Not that long, actually, 500 days, but it's long enough to give you an idea. So you have this dry patch over northeast for a positive-negative dipole, and you have a wet patch for a negative-positive dipole. So this dipole, this Atlantic dipole, people talk about it. Since I did this work, I've kind of come to the understanding that the Atlantic dipole doesn't exist. If you do an EOF analysis of the SSTs in this region here, you'll get a dipole. But that's just because EOFs all they do is collapse the data into the fewest number of patterns, right? If you look at the correlation between this point and this point, there isn't any. So you can have all the elements of these dipoles, but they don't really depend on each other. The correlations are much more between these regions and the extratropics. But anyway, as an academic study, this is informative. And so this is still with an equilibrium response. Let's try some forecasts now. So now we have a run which starts at the beginning of January and runs to the end of May. And we use the last 3 months as our verification period. And use the, so here's the control for that. It looks very similar to the equilibrium run. But this is just a single March, April, May now. Our initial condition was the 1st of January, 1979. Why 1979? Because that's just the first point in my data set. Right? So the pattern hasn't changed. We still have this dry patch here, then wet, and then this wet patch here. It looks fairly asymmetric, though. It doesn't look like this is really the opposite of that. So that's interesting. It makes us wonder, are there important nonlinear processes going on here? Or is this just noise because we've just done a single forecast? So to answer that question, we do an ensemble of forecasts. So I have, my data set is from 1979 to 2016. So that gives me 38 1st of Januaries to play with. So I'll take the mean of all of those. I'll do 38 forecasts, right? And take the mean of that ensemble of forecasts. And now this is the ensemble mean result. There's the ensemble mean climatology for the precipitation. Here's the ensemble mean response to a warm, cold dipole. You have a dry patch here and wet here. Here's the ensemble mean response to a cold, warm dipole. It looks a little bit more symmetrical than it was before. So some of that was just noise, okay? But it's not, it's still nonlinear, but it's not as nonlinear as that. So that's our idealized kind of, this is all kind of training for the serious job of doing seasonal forecasting, right? So then what we need, instead of having these idealized SST anomalies, we need to start using real SSTs, okay? And that was the big model development of last year to get that all into place, with O'Baines and Junio especially. So let's go back to our forecast for 2022. Now you know how we did it, right? It's an anomaly forecast using a simple dynamical model with an empirical prescription to go from the SST to the tropospheric heating. The model responds with a convection scheme. And this is our this is our JFM mean. So let's apply that to every other year for which we have SST data. So what we do here is we take the SST anomaly for the beginning of January, and we persist that anomaly throughout the forecast. So the anomaly remains the same. The climatological SST, which you could see actually was important in the transfer function, that can develop because it follows the annual cycle. But the anomaly itself just stays the same. And so if you do that for every year in our data set, so we have data for SSTs since 1982, right? So we said, let's do 1982 all the way to 2020. So that's 39 years of hindcasting. Each year, you have to do 38 members in your ensemble. So that took a while. And the result is you could plot the correlation between the observed the observed precipitation anomaly and the forecast precipitation anomaly, right? And so blue is good, red is bad, okay? So you can see that over a lot of the northeast of Brazil, we're quite good. Not so good over the very northeastern tip of Brazil. We do a good job generally in a lot of the tropics. Not surprisingly, we're quite bad in the extratropics. The problem with correlations is having no rainfall at all in the model correlates very well with having no rainfall at all in the observations. So it would be much better to have a diagnostic that really focuses on the place where it's actually raining. I'd rather have had a covariance plot here, but I don't have that, right? So let's focus in then on the region we're interested in, which is this box here, northeast Brazil. So that's our nordeste box, right? Now, there are two ways of doing a forecast. The way I've described, in which you take the 1st of January SST anomaly and you persist it throughout the forecast. And the other way in which, God, have I already talked for more than an hour? No. Okay. No, okay. So yeah, there's the other way in which you, if you're doing hindcasts, you can cheat, right? And you can allow the SST anomaly to develop during the forecast. So it's not a real forecast. For the 2022 forecast, of course, we couldn't do that because we can't see into the future. That's where Yogi Berra's quote comes in, right? For hindcast, you can do that. And so I'd like you to look at these graphs. So the solid black curve, actually there's two of them for two different data sets, is the observed precipitation anomaly in this box. And the kind of box plots here show the range of the model ensemble. And so the question is, how good is that? How good is this model? To your eye, do we see anything which looks like it corresponds to the observed anomaly? So these are anomaly plots. We've ignored the bias in the model. And you know, you can kid yourself that there are times when it's doing well. Or you can say, well, it's not much different to just throwing a three-sided coin, right? And then you would expect this one, the developing SSTA runs, to be a bit better than the persisted SSTA runs. The proof of the pudding, right, is in what we call the confusion matrix, right? So we have dry, normal, wet observed here, dry, normal, wet for the model here. And what you hope is that most of the cases, year by year, will fall on this leading diagonal, right? That's not quite what happened. So, yeah, we do quite well predicting when it's wet. We do pretty badly to predict when it's not wet. We say it's going to be normal, right? But by and large, I would say that this is not much different to random. This is slightly better, but is it significantly better? I don't think so, right? So there's clearly still work to be done in trying to maybe tune our SSTA transfer function, or look in detail at different processes to see what's responsible for what in the model. And that's why at the beginning I said, this is a research tool, and we can use it to do research. It complements the forecasting system. Now, seasonal forecasting is a very difficult problem, especially in a limited region, okay? So a proper GCM is not necessarily going to do much better than this either. So the bar is quite low in terms of what you call success. But what I'd like to do just at the end here is start trying to attribute causes, okay? So to do that, I've concentrated on these 2 years. Right, so 2006 and 2007, they're slightly different. And in the observations as well, 2000 oh my God, have I got that in the wrong place? So 5 and 6. It's 5 and 6. Yeah, sorry. But it shouldn't be. Shouldn't be. It should be 6 and 7. That I think somehow that I definitely did 6 and 7. Right. So I'm going to just correct that right now, because that would be very embarrassing to. I'm going to move that over there. That's what I wanted to say. Right. There it is, 2006 and 2007, which in the observations and also in the model, 2007 is slightly drier than 2006. Okay, so then we can ask the question, why is that? Why did the model predict slightly drier conditions in one year compared to another? And the answer must be in the SSTs, right? That's what's changed between the two. If it's deterministic at all, it'll depend on that difference in forcing, right? So this is the SST anomaly for 2006. It's a La Nina with a dipole in the Atlantic. This is the SST anomaly for 2007. It's more like an El Nino with a warm Atlantic. This is the model rainfall difference, 2007 minus 2006. And it's a bit dry over northeasterly Brazil, as you'd expect from what I saw on the graph, on the box plots. It's wet over the Pacific. There's a bit of a dipole over the Atlantic. It's wet over the Indian Ocean. So this looks like a La Nina response, but sorry, an El Nino response. It's a relative El Nino response. So that makes sense. Okay? Everybody expects it to be wetter in northeast Brazil during La Nina, drier during El Nino. So that kind of figures. So I run the model again. So this is two 38-member ensembles compared. Do another two 38-member ensembles, but only force over the Pacific. Pacific only. What do you get over northeast Brazil? Well, that's interesting, isn't it? You get actually a bit wetter. It's a bit confused. Right? All right, do the same experiment with just the Atlantic. That's where you get the dry anomaly, you see? Same experiment, just the Indian Ocean. Well, not much, okay? So the Atlantic is important. Even when you're comparing an El Nino year with a La Nina year, the Atlantic turns out to be important, at least in this model. All right, so that's interesting. And also it's interesting the extent to which I haven't actually produced that result, but if you add these three results together, do you get this one? Well, I'm not sure. I think you probably get something fairly close. Anyway, that's my last result. So to get this result, I had to run this laptop for 24 hours. And I did that last week. That's as far as I've got. Oh, hang on a second. No. I've just been misleading you, right? So these results here are not for ensembles. These results here are for single-shot forecast runs. So this is a run in which I take the 2007 SST anomaly, and I initialize that run with the 1st of January 2007. And the other one, I take the 2006 SST anomaly and initialize that run with the 1st of January 2006. So these are simple, naive forecast runs, right? Then you repeat it with the ensemble to see how robust that is, that conclusion. And the answer is yes, it's quite robust. You get a drying here for the Atlantic. Oh, but you also get a drying for the tropic. This drying here comes from the Atlantic. Slightly wetter if you only use the Pacific. So yes, that is a similar conclusion to what we had with the single initial condition. Right? It's a good thing I'm practicing with you guys, because I'm going to do this in New Orleans next week, and I'm going to be perfect. Right? And the Indian Ocean doesn't matter, basically. So there you go. That's my punchline. And so a few conclusions. We have produced a successful forecast for 2022 at a bargain price. It's an order of magnitude faster than a GCM forecast. Right? So DREAM can be used to complement existing GCM forecast for South America. The speed of operation, the simplicity of diagnostics can be an asset for an alternative forecast design. If you want to do experiments to figure out how you should do your forecasts, this is a test bed. The method of anomaly SSTAs and associated deep heating gives consistent results across a range of model complexity. So I've shown you time-independent dry dynamics, time-dependent dry dynamics, moist thermodynamics. They both amplify the signal over the continent. We have some systematic errors, but DREAM has a reasonable interannual variability in the forecast precipitation. Hindcast skill is limited. That's my diplomatic way of saying it's rubbish. When you look at measures based on rainfall classes, okay, there are other things to look at. And it's quite a tough test to look at such a small box in the corner of a continent. Right? The Atlantic sea surface temperature anomaly seems to play a crucial role, even in years with contrasting Pacific SSTAs. More work is needed on the SSTA transfer module, and we'll guide that with examples from hindcasts like the one I showed you. If we can improve the hindcast skill, then we can carry on and think about using DREAM for applications like hydrology. I haven't talked about hydrology, but there are people at FUNSEMI who are interested in using DREAM output to run hydrological models. And it's also a useful research tool for institutes with limited computer resources. So that's my kind of IRD ticket. I'm funded by the French Institute for Research for Development, which cooperates with a lot of countries around the world, which might benefit from having simpler, cheaper tools for forecasting. And that's it.
Thank you, Nikki. Now, bom, português, né? Ele entende. Perguntas, comentários, sugestões? Alguém tem alguma pergunta? Dúvidas? Vocês estão me ouvindo? Então, né, aqui. E será que dá para ouvir aqui? O Fábio falou que não estava ouvindo uma hora. Alguma pergunta? Nick, one slide you show that the wind, the jet is stronger, but the storm effect are weaker.
Yes. Yes, that's right. Yeah.
What is the link? Normally, we think that the jet is strongly more storms.
Yeah, that's a very interesting question, because I think one way to look at it is in terms of the momentum balance, the zonal mean momentum balance. Right? Now, normally you think of the transient eddies with momentum flux convergence feeds the jet, accelerates the jet. And the net force on the jet is to the west, right? Okay. Which is balanced by the Coriolis force pushing the other way on the ferrule cell, right? Okay. Now the model has a weak ferrule cell and weak eddies. Oh, okay. So the jet is unconstrained. And this is consistent with the fact that at the lower levels, it has a weak jet, has a weak surface wind, so that the balance in the lower levels is normally between drag and the Coriolis force, with the ferrule cell going the other way. We have a weak ferrule cell, but we don't have much drag either, because we have weak westerlies at the surface. So it all hangs together, that you have weaker transients, weaker surface winds, a weak ferrule cell, but the jet is unconstrained. Okay? So the jet is actually stronger, but that just because the mean wind is stronger doesn't mean that the momentum flux convergence has to be stronger. Okay? And why does the model fix on that balance? I don't know. We don't impose the balance between the transients and the mean flow. All we impose is the total residual momentum forcing. Right? So the model can choose what balance it goes to, and it chooses that in the southern hemisphere.
Okay. Okay, thank you. Question? Mais alguma questão?
Mas tem alguma pergunta no YouTube? Vocês conseguem ver? Eu não consigo ver com o meu celular. Enquanto eles olham, you showed the correlation between forecasting in for our South America, the blue, red color.
Yes.
This one. But you check for seasonal only here. This part you don't check yet because of
No, we've done some runs where we look at before kind of November, December, January.
Ah, sou eu.
So I got to stay away from you because this is the kind of automatic COVID warning. You know.
Here is for May, March.
This is what is this? March, April, May. This figure. Yeah.
Okay.
So what it means is that if you're looking down here, there's not so much rainfall anyway. So this good result might be misleading. That's why I hesitated to show this.
This is a
slide.
good result because the seasonal forecasts are very bad.
Yes, but this is a seasonal forecast for March, April, May, right?
Okay.
What you want is a seasonal forecast for November, December, January. Yeah, and we have those forecasts.
Okay.
But I've kind of tuned this talk to the northeast. So
Okay.
so maybe I should. I have some. I think I have a slide. Oh no, not that one. Oh yeah, there it is. There. There's a November, December, January result for I think that's for. This is for persisted SSTA, and this is for developing SSTA. And you can see that now this is just the anomaly, and this is the rainfall.
Okay.
But in fact, DREAM has a dry bias. Okay. So can you correlate in your head between? So this box here is kind of.
Midwest of Brazil.
What's happened here? Oh, I need to play it. I need to play it. Oh, I need to fit it. There we go. So this box here is kind of here, right? And so let me just go back to that slide. You see, it's not finished. It's not properly put together, this slide, but I don't think it corresponds very well. If you look at the contingency matrix, it's no better here. But this is work in progress. Okay, so we don't know for sure.
But this region is too difficult to this one. This here.
Yes.
It's not
This is what Junior tells me is that the ECAM model.
the worst region of South America too.
The ECAM model performs very badly in that region,
Yes.
and Junior tells me that DREAM is better than ECAM, which is perhaps not saying much, but.
Nick, one of your conclusions is that the Atlantic. One of your. Now, one of your conclusions is that the Atlantic is important for the precipitation in the northeast of Brazil, despite of if you have SST variabilities in the Pacific, for instance, Neo.
Mm-hmm.
And but I think you are aware that we know that for a long time there are lots of works, observational works, and also correlations about this region, isn't it? Yeah. So what you are saying that is your model is going the right direction and showing that the Atlantic is quite important for the forecast over the northeast Brazil. Is that?
Yeah. Well, I mean, this is just based on one comparison between two particular years, right? So I'm not trying to generalize, but yeah, it's in line with that conclusion. Yeah.
If you have a strong El Nino, I mean, if you have a strong El Nino event, like But doesn't it depends on the magnitude of the forcings, like the SST forcings? I mean, comparing the Atlantic, the magnitude of the SST anomaly in the Atlantic and in the Pacific.
Yes, I mean, we're using observed SST anomalies here. So the transfer function will respond to whatever strength anomaly there is. There's no normalization of the anomalies here. So, what we need to do is look at years where there's a strong El Nino as well. We have a whole bunch of cases to study, right? With this, breaking it down by ocean basin approach. This is just the start. But I think there's probably going to be some sort of threshold effect where El Nino becomes important at some point. And I think the simplest way to look at that is just through case studies, year after year. So at Prinsemi, using the Prinsemi system, we should run through the whole forecasting thing 4 times. It's going to take a while, but there's a lot of experiments to do and a lot of analysis to do afterwards.
Yeah, there's a paper by Souza and collaborators that has done this correlation between the tropical North Atlantic, tropical South Atlantic, and the SST in the Pacific. And they show when one dominates over the other along of the year.
Yeah.
It's a paper from 10 years ago, but it's quite interesting results.
Yeah.
And I think we can use this kind of guides to see if your
Well,
model is
I mean, what we can do with a large number of ensemble experiments in which we have model results with all the dynamics, we can be much more systematic than you can with an observational study where you're not quite sure about stationarity. And we can actually look at mechanisms. We can look at all the humidity fluxes or the preconditioning. We can look at all the dynamical entities we want to in those ensemble mean patterns. But the trouble is that I think it has to be couched in just understanding the model's behavior, because as you saw, the model doesn't always get it right. So we can't necessarily say this year it happened like that, because it didn't, right? You have to be aware that we have 38-member ensemble in the model. In the real world, we have a 1-member ensemble. And so I think another interesting question is the times when the model gets it wrong. Was there at least 1 member that got it right? I mean, that's another question.
Yeah, the good thing is the model is simple compared to a GCM, so it's much easier to find where the model is going wrong.
Well, you'd expect that to be true, but the other thing is you can also do a lot more experiments than you can with a GCM. So you can home in on what your problems are.
Yeah, true.
Ok.
Bom,
Você quer perguntar? Eu ia encerrar.
última pergunta.
Have we got any questions from the internet?
Não.
They've all
No,
gone. They all gone.
Tem pergunta ou não? Não. No, if I don't know if I understood correctly, but I mean, if I did, the idea of your approach is to extract the signal, the main, the signal of the main forcings, right? For the I don't know, for the precipitation anomalies at the northeast, right? Is that so? Like the sea surface temperature anomalies in the Atlantic, right? But if you don't have any clear signal of, if you don't have an El Nino or you don't have significant anomaly at the Atlantic dipole, I mean, your prediction would be dependent on the internal dynamics and what
Well-
about the predictability?
Well, I mean, if you don't have anomalies in the SST, then you don't have anything which will allow you to make a seasonal forecast.
Yeah, yeah,
That's true for any forecasting system. It's the only thing which is persistent over that timescale. So if there are exceptional years in the absence of that element, then those exceptional years are unpredictable. That's what you have to
Yeah.
assume. And this is all we can do.
yeah. Okay, good.
Ok. Thank you.
Bom, vou encerrar o seminário. Sexta que vem tem outro seminário que eu não me lembro qual é. Obrigada.
Thank you. Thank you for coming. It's nice to break the ice.
Acho que a Natália Pilates desse seminário.
Right, so
Sexta-feira? Ixi.